So hello to all of you. My name is Sachin, and today in this video I'm going to talk about a substitution reaction. And basically in substitution reaction we have many type of reactions that we are called Sn² reaction, Sn1 reaction, SN reaction, and basically last one more SNI, nucleic substitution internal reaction. And in this topic I'm going to start with Sn2 reaction, then we will take back forward with the Sn1 SNNGP. Okay, so let's start with the Sn2 reaction. And in the Sn2 reaction, we called it nucleophilic substitution, but we called it nucleophilic substitution by molecular reaction. We called it nucleophilic substitution by molecular reaction. And first, we take the brief idea what are the reactant and what are the nucleophile we are going to take and what is our product in this reaction. So the reactant we are going to take is alkyl halide. I am going to take the reactant is alkyl halide. So this is our alkyl halide nature. This is my alkyl halide, and the nucleophile I am taking is NaOH in this. And what is the product we are getting? I am already giving you idea that we are getting inverted product, and what the product and we are getting it, we are going to see in this reaction. So NaOH is having ionic compound Na plus OH minus. So this carbon chlorine bond have a leaving tendency. So this carbon, due to the En difference, this is having partial positive and this is having partial negative. This carbon chlorine bond have a leaving tendency. What I am saying is it have leaving tendency, but not leave at its own. Not leave at its own. Okay, so let's start it. First I am saying that this carbon chlorine bond have a leaving tendency, but this bond not leave at its own. And how it is leaving? When the nucleophile, this is our NaOH nucleophile, when the nucleophile approach it and give the electron density to the carbon and Cl group leave it, then it is called nucleophilic substitution by molecular reaction, and we are getting our inverted product. And what is the mechanism behind the reaction that we are getting inverted product? We are going to see that. So let's start with the mechanism. This is our alkyl halide. This is our H bond, and these are our next hydrogen, and this is our carbon chlorine bond. And there is a polarization in carbon delta plus Cl delta minus. And you all know that this chlorine bond is also having some electron cloud around this, and these are the electron cloud of hydrogen. And first the nucleophile going to approach it, and the nucleophile is OH minus. The OH minus will approach it, but there is a sort of electron repulsion. That is, there is sort of electron repulsion in the electron cloud of Cl and OH, because this Cl is the biggest group. What is this? This is our biggest group. So this path is not favorable for the OH minus to approach it the carbon from the front side. So then the OH will going to approach it from the backward side, that is from the 180-degree angle to the leaving group. So this is our leaving group, and OH is approaching to the back side, like to the 180-degree angle. So this path is not followed by OH. So then what OH is going to take? The OH minus will going to approach it to the back side, and in the back side it is approaching in what orbital? We are going to talk about that. It is approaching in the carbon CCl antibonding orbital. Okay, so the student have doubt also asked me about many times, sir, there are many types of orbital in this, like carbon hydrogen vacant orbital, carbon hydrogen and carbon Cl. So we have, there are two types of vacant orbital, that is we call LUMO, lowest unoccupied molecular orbital. And I say that the antibonding orbital with lowest energy is called LUMO, and nucleophile first approach in this. So this is our LUMO, lowest unoccupied molecular orbital, and this is our Bent rule. Then the Bent rule say that the electronegative atom going to decrease the size and the energy orbit of the orbital, and Cl is our electronegative atom. It is going to decrease the size of orbital, size and the energy of the orbital. Okay, so the nucleophile approach from the back side to the anti-bonding orbital of carbon chlorine bond. Okay, So when this carbon chlorine bond anti-bonding side approach, this Cl bond is going to leave it, and there is the we are going to see that there is a simultaneous attack. Like all the things are take place in one step. This is our simultaneous reaction. What is we called it? Simultaneous reaction. In this, that is one step reaction. We also called it one step reaction. Like bond breaking and bond forming all are done in one step. Like OH minus attacking from back side, it is going to form a bond, and the Cl is also leaving from front side. So this is a bond breaking, and the all the things are keep behind the transition state. And what is happening in transition state? There is particular a carbon we have, and the nucleophile approaching to the back side, and the Cl group leaving from the front side. So there is maximum two things are approaching to the same orbital, and from this nature the hybrid orbital of carbon is going to convert into the atomic orbital. Okay, so I am going to represent it. What are things happening? So this is our hydrogen, the front one. This is our hydrogen from the back side, and this is our also one hydrogen, and this is the orbital we have, and the nucleophile is going to approach it from this, and the Cl is also approaching to this one, and there is our electron density delta minus and delta minus 1. This is our transition state. Okay, so let's see it. This is carbon is having sp2 hybridization. Okay, because it is not sp3. Some students say it is sp3d, but beta it is not sp3d, because the carbon is having only s and p orbital, not d orbital, because d orbitals are a very high energy. Okay, so that's why carbon is only having s and p orbital, so its hybridization is sp2, and this orbital is not hybrid. This is our atomic orbital. This is 3 centered 4 electron bond. This is 3 center 4 electron. Okay, so let's see what the product we are getting. We are getting a product from the back side. Like nucleophile is approaching from back side, so we are getting the nucleophile to the back side of carbon, and there is inversion is going to take place in this reaction. See the product. There is an inversion take place in this reaction. There is inversion take place in this reaction, and I am going to say that, sir, there is inversion. Like how it's going to happen? When the nucleophile are attacking to the back side of the carbon, this hydrogen bond are going to shift to the invert side, and we are getting the inverted product. Okay, so let's take the notes and summaries of the points we are going to tell. Okay, so let's first talk about the rate of reaction. Okay, the rate. First talking about the RDS step. This is our called RDS, the rate determining step. I will going to give you the brief idea about RDS. Okay, so RDS is the step which is called the slowest step in the reaction. What is called RDS? RDS is called the slowest step in the reaction, and this RDS is going to keep it called slowest step. What is this? Slowest step. And why is it is slowest step? Because when you are going from a stable to the unstable one thing, because this is a stable product, our reactant, when the nucleophile approach it, there is sort of electron density, and the hybrid one is converted into the unhybrid one. So transition state, in this we are getting the RDS. Okay, and in the RDS one there are two things we are seeing. First the nucleophile, and there is the alkyl halide. So in the RDS, the slowest step, we are getting, what are things we are getting? So the rate of Sn2 is equal to rate constant of Sn2, and we have two things, one in our alkyl halide and second thing is our nucleophile. So there are two molecules are involved in our RDS, one is nucleophile and one is alkyl halide. So it is called a bimolecular reaction. What is called? Bimolecular reaction. And in this order, what is the order of reaction? Both are having a single order with respect to alkyl halide, and this is also having first order with respect to nucleophile, and the overall order of the reaction is second. So the what is overall order of reaction is second order. We said second order reaction. Okay, So let's collect the brief points. Inversion in the product, nucleophile approach to the backside, simultaneous reaction. RDS is our this is our biomolecular reaction because the two mainly things, alkyl halide and nucleophile, are involved in the reaction, and the rate is our second order reaction. That's why we called it nucleophilic substitution biomolecular reaction. Okay, so let's think about it. There is kinetic isotopic effect we are already studying. Okay, so the kinetic isotopic effect is going to affect in this reaction? No. Why? Because kinetic isotopic effect, what the things are involved in KIE, kinetic isotopic effect? In the kinetic isotopic effect, okay, I am going to rub this side also. In the kinetic isotopic effect, what is kinetic isotopic effect? If we replace, what is this? If we replace our bond with the hydrogen isotope, that is our deuterium and tritium, but is there any effect on the rate of the reaction? Because the carbon hydrogen bond breaking is not involved in the RDS, so kinetic isotopic effect is not going to observe here. So no kinetic isotopic effect. No effect is observed. No effect is observed because no bond breaking of carbon hydrogen in the RDS one. Okay, and there is also called element effect. What we call element effect? That is the leaving group is the leaving group leaves in the when the leaving group leave the reaction, is it involved in RDS? Yes, the leaving groups involved in RDS. Okay, so element isotopic effect is observed. And what is the potential energy diagram of this reaction? What is the potential energy diagram of this reaction? We said our potential energy. Okay, we said our potential energy, and this is the progress of reaction. This is the progress of reaction. This is our reactant, and this is a one-step reaction. So the graph would look like this. Graph would be look like this. Okay, the product is going to more. The reaction is going to be because. Okay, the one more point I can tell you. This is our reactant. This is our product, and this is the transition state. What we called it? Transition state or activated complex. We called it activated complex. And this reaction is exothermic in nature. Why it is exothermic in nature? You all going to take the idea exothermic reaction because first we have carbon chlorine bond. Okay, and secondly we have carbon oxygen bond, and this nucleophile is OH. What is nucleophile is OH. So this is our 2p 3p overlapping. This is our 2p 2p overlapping, and this overlapping is much stronger than 2p 3p. So a strong overlapping is going to happen in this strong overlapping. So let's see the strong overlapping is happening here as compared to the weak overlapping. First we have in the reactant. So the graph would be exothermic reaction, and product energy is down from the reactant. Okay. So let's take the 1-2 point also. What we call the notes of this reaction points. Notes points of the reaction. Let's see. And what are the factors that are affecting the Sn2 reaction? Okay. So first let's think about it. This is the Sn2 reaction. Sn2 reaction is take place when some nucleophile is going to approach on the back side of the reactant molecule and going to leave the and reactant also, and in the reactant the leaving group also start leaving from the reaction. Suppose कि when this reaction is going to take the fastest, it is going to be fast when the nucleophile when coming to the back side, it is having the minimum repulsion, like it is facing the minimum repulsion from the other reactants of the in the molecule when it is approaching to the antibonding orbital of carbon chlorine bond. So the first point is less steric hindrance will allow the more rate of reaction. What is it called? Less steric hindrance. Less steric hindrance have more rate of reaction. Have more rate of reaction. Like I am going to tell you in the this pattern. This is our hydrogen. Okay, and now I am going to replace one hydrogen with CH3 group. Okay, now I am going to replace this hydrogen with CH3. So I am going to rub this portion also for explaining this criteria. And there is, I am also taking one more case when we have 2CH3. Okay, so let's start. We have anti-bonding orbital here. This also having anti-bonding orbital, and this is also having anti-bonding orbital. So let's think about it. When the nucleophile OH minus is approaching to the back side of all these three molecules, when it is approaching to the anti-bonding orbital, when it approaching anti-bonding orbital. Okay. So when this attack will be more favorable, because this is our electron density, and the more smaller is the hydrogen, more favorable to attack from the back side. This CH3 bulk group, this will repel the OH minus to come from the back side. Okay, so this attack is favorable. This attack is also favorable, but this is where Sn1 reaction take place. This is the most important thing when Sn1 reaction take place, because it is approaching the backside and two bulky methyl groups are going to give the steric hindrance to this upcoming nucleophile. Okay, so then what is going to happen? The CCl bond is not destroyed by on, but if we create the more hindrance to the backside of this carbon, like MECC3 group, so then this bond is going to repel with the carbon chlorine bond, and the CCl group will start dissociating, because the solvent is also favor the dissociation of carbon leaving bond. Okay, so then we are carrying about Sn1 reaction.